chapter 1, section 1.5, boom. We are on now elementary matrices and a method for finding the inverse. So we did an inverse on what kind of matrix? Square 2 by 2. Well, not anymore. This is to your question, how in the world do we find inverses for other size matrices? But first, we got to recall our elementary row operations. First, do not forget that you can multiply a row by a non-zero constant C. You can interchange two rows, or you can add a constant C times one row and then add it to another. So we have done all of those things. All right, so let's just say here's your definition 1. Matrices A and B are said to be equivalent if either, hence each, can be obtained from the other by a sequence of elementary row operations. So if I can do some elementary row operations on A and I can obtain B, and then, or if I can do the reverse, I can do some elementary row operations on B and get A again, then those are going to be row equivalent. So here's a new definition that you're going to want to take note of is what is now an elementary matrix. So we had identity, we had zero matrices, we had identity matrices, and now we're going to have an elementary matrix. So this is, here you got to be very careful about your definition. So a matrix E is called an elementary matrix if it can be obtained from an identity matrix by performing a single elementary row operation. This, you have to be very careful about your definition. You will notice that you have to do it, it has to be obtained from an identity matrix. Does everybody remember what those are? So you have to recognize what is your identity matrix, and then you can only perform a single row operation. So you're gonna have to remember, what are your row operations? So here, let's see if you can figure out what has happened. So if we go from this identity matrix to this elementary matrix, so here we can see it's identity matrix, it's square. We have a diagonal of 1s, the rest are 0s. How in the world do we go from this identity matrix to this one below it? Can you identify the row operation? Yes. Oh, is it? What do we think? Yeah, the bottom one is just multiplied by a -3. So that would be one of your row operations. But I like your thought, because you're gonna have to figure out which ones they do that. Okay, what in the world has happened with this next set? How do we go from this identity matrix to this one? Yeah, but which ones did we move? Yeah, so it's how quickly can you see this? So this one and this one got interchanged. Not everybody can see that one right off, so it's interesting. All right, what in the world happened with these? What were you saying before?
Multiply and add.
Okay, so what do you think happened in that third column?
What happened here is 3 was multiplied by the last row and then added to the top.
You got it. So that's what happened to that one. And then what happened in this last column? Yes, you multiply by 1, any of the rows. So defined by a single elementary row, by a single row operation. Okay, not more than one, just one operation. Now, if you just realize that you can do the inverse. So if for say you did a row operation on I that produces E, then you would do the reverse or the inverse operation on E to reproduce I. So if before you multiplied a row by I by C, that doesn't equal 0, to flip it back and get the inverse again, well, now you'd have to multiply that row by 1 over C to get your original matrix back, right? So if you did a row operation on the identity matrix where you interchange those rows I and J, well, to get your identity matrix back from that E that you just created, well, then you go ahead and interchange those rows again. And then to get to produce E, if you added C times a row I to row J, well, to get your identity matrix back, you would then add -C times a row I to row J. So you guys see how you're doing the inverse operations to be able to flip between I and E matrices. So this is going to be a key slide that you might want to go ahead and bookmark. So here, what are we doing with this one? Yeah, so here we multiplied the bottom row by 7. So multiply bottom by 7. So this was what kind of matrix? This first one is what kind? Yep, that's your identity matrix, I. You did one operation to get E. Now you're going to have to do the inverse operation to go back to I. So what would you do to go from E back to I? Yes. So here you have the inverse by multiplying by 1 over 7 instead. So you see how that works? You're going from I to E and then back to I with one operation for each of those steps. Okay, so let's look at this one. Okay, what did we do for this one?
Interchange.
Yep, you interchange those two rows. Well, what do? You just swap them back again to get your I again. And then the last one, let's do this. Your inverse operation. Ooh, what did we do to this one? Ooh, how did we go from I to E here? Yeah, multiplied bottom by what? Okay, by 5, then add to first row, right? Ooh, how are you going to get back to I? What do you guys think? What was that other one you can do? Well, let's go back to this slide. Go back to these. So if you added C times a row I to row J, then what are you going to do? To go back.
So -5 times.
Yeah, so that means, what are you doing? Yeah, so now you're multiplying the bottom row by -5 and adding it to the first row. And that'll get it back. Bottom by -5, and then add to first. So those are going to be your inverse operations. Yes, go ahead.
When we are converting from inverse to the equation, like, are you gonna tell us what change we want to make, or how do we know how do we know that we have to do it like 5? Are you gonna tell us, like, convert from inverse to?
No, I'm going to give you a matrix and be like, what did we do?
So you're gonna
Right?
give us the.
So you got to figure out what happened, right? And then you're going to need to know how to use the inverse operation to get it back to the original I.
So you're not gonna answer, for example, to convert from inverse to the.
I'm going to give you, say, like 2 matrices here, like we did here. See how we went here? Like, how did you get from this matrix to this matrix? And you'd have to recognize what operation you did. And you'd have to, or I might give you the bottom matrix and I might say, okay, what operation do you have to do to get back to the identity? We were looking at 1.5 elementary matrices. So please remember what your elementary matrices were. Anybody want to yell it out really, really quickly?
Change one. It's just like an identity matrix that has like.
Yep, identity matrix where what has happened? Only one elementary row operation has happened to change it into that elementary matrix, I should say, singular. Okay, so the other part of this particular, let's see if I can splits. Oh, sorry. All right, and let's move that over. Okay. So the one other thing that we need to go over in this particular section is we had talked about before how to do an inverse of a matrix, right? But under what conditions was that? Does anybody remember? Ooh, so what happens if your determinant equals 0? No inverse. What happens if it's not 0? There is an inverse. You just got to find it, right? What kind of matrices were we looking at?
2 by 2.
Ooh, we're working at 2 by 2, which is also what? Square. So you're gonna want to remember all these properties. So now we've got to look at what in the world happens if we want to work with matrices that are more than a 2 by 2. So we have in section 1.5, we have some things that you're going to want to know. So theorem 1.5.3. This is an equivalent statement. That means that the following statements are equivalent. That is, all are true or all are false. So this is a pretty handy theorem when you have these equivalent statements. That means you only need to pick out one of the statements that is useful to you, because you know if you can prove that one statement, then you know the rest will also be true or be false, depending on which one you have picked. So you want to start looking at these. So if you look at a matrix and it was 2 by 2 and you found that its determinant did not equal 0, well, then you'd be able to say to yourself, oh, that matrix is invertible. Well, guess what? If that matrix is invertible, it means that AX equals 0 has only the trivial solution. It means that the reduced row echelon form of A is going to be an identity matrix. So you could also be able to then say that A is expressible as a product of elementary matrices. So all of that stuff is great. So that is a really useful part of equivalent statements. Has anybody ever worked with those before? Okay, so keep that in mind. This one happens to be an equivalent statement. Yes.
Yes, part B mean the trivial solution.
I am so glad you asked that because we're going to be looking at that. So hold on to your seat on that one, okay?
I apologize.
Mhm.
So that either means, so it's not that if, okay, never mind, I got it.
Okay, so either they're all true or they are all false. So when you're looking at something, you're going to want to use these equivalent statements advantageously. If you can immediately determine that a matrix is invertible, then you're going to know, oh, well, then I know that this only has a trivial solution. And that's going to save you some other work. So some of these statements will be easier to answer than others. And so you want to strategically pick them, and then that way you'll be able to make other assumptions about your matrix. Okay, so we are going to be looking at, here is going to be your method that you're going to want to use if you have a larger matrix. So before we were working with 2 by 2, and we had that nice little equation where the inverse equals 1 over AD minus BC times the matrix where A and D were switched, and then you have minus negative B and negative C. So that was 2 by 2s. Now, if they are larger, so here it is, theorem, Here's what you're actually going to do. This is going to be what you're going to be able to do if you have a larger matrix. So this one is a 3 by 3. So we wouldn't be able to do those things that we learned last time, would we? So the technique is going to be, if you looked at example 4, if you have a larger matrix, what you're going to do is right next to that matrix, you're going to set it up and you're going to put an identity matrix right next to it on the right side, but it has to be an identity matrix of the same size. And then you're going to go through elementary operations on both of those together. And what's going to happen in order to obtain that inverse is that once you've done enough of those operations to achieve the identity matrix on the left, the resulting matrix on the right is now going to be your inverse of A. So does that make sense what I said? Yes, go ahead.
How do we know if A is invertible if it's greater than 2/2?
If it's greater than 2, this is going to be whether you're going to be able to determine whether or not it is.
Also, like you're doing this to know.
Yeah. So here's finding out whether or not it's an invertible. And if it is, what is that inverse? So by 2 by 2s, we had a very easy method, right? We right away could look at the determinant. And if it wasn't 0, we'd be like, yes, it is. This one, we're doing a different technique. Yes.
The vertical bar that separates the A and the I, what did that represent?
Yeah, that means that you're creating a larger matrix and it's partitioned into 2 separate submatrices. So one of them is the A matrix that you're trying to determine if it's invertible and what the inverse is. And then the other submatrix would be your identity matrix right next to it. And now you're forming this much larger matrix to solve. Yes.
So the idea of taking A and then doing the operations on it to form the identity matrix, and then performing those same operations, same order to I.
Yes. You're doing them side by side at the same time. So you're making a much larger matrix, and you're doing all of the same elementary row operations on both of them at the same time. So we're going to see what that looks like. So you guys ready? Here we go. So if we wanted to find the inverse of this, our first step would be is we're going to create this much larger matrix. We're going to draw that line to show the partition between the 2 submatrices. So on the left is your original A that you're trying to determine if it's invertible and what that inverse is. So what you're going to do is you're going to plop this identity matrix right next to it to form a much larger combined matrix. So does everybody see that this is identity matrix? It is also square of the same dimensions? Yes.
So we usually use the power of 1 to show that. So in this case, why do we have
Because that I is helping us be able to determine if that matrix is invertible and what that inverse is. So by adjoining A and the identity matrix and then doing operations on both of them simultaneously, at the end of all our manipulations, we're going to end up with I on the left and the inverse of A on the right.
So that I is not there, it's not something.
As a result of all the different row operations we're going to do, at the end of that, if it's invertible, we'll get I on the left, and we're going to get the inverse of A on the right. So this is a methodology that we're learning for larger than 2 by 2 matrices. Yeah, so if it's larger than 2 by 2, you're going to have to use this. So you're going to look at A, and you're going to want to ask yourself, well, how in the world am I going to get this into reduced row echelon form? So you guys should already know how to do that, right?
Yeah.
So I think if you look at example 4, you're going to see, so if you're kind of looking at this, what would be like one of the first things that you'd want to do?
Get zeros underneath that first.
Yeah, you want to have this be your leading one up here, right? So one of the things they suggest is to tackle this bottom row. So keep in mind, you'll be doing operations across this whole entire conjoined matrices now. So bless you. Bless you. So you're going to strategically pick the operations that are going to reduce this A into reduced row echelon form, but you're going to be doing the same things on I on the side. So here you would want to do what? You would want to do, what do we want to do to get this 0 in the bottom row? What would you do?
Make the first row by -1 and add it to the third.
Exactly. So you do -1 times that first row all the way across, and you'd add it to the bottom row. So if we look at our next one, so you should go ahead and get this from here. The other operation that you'll also want to think about is getting rid of that 2, because you got to turn that into a 0. So you would do -2 times that first row and add it to the second row. Keep in mind, you go all the way across. So now you can see how that identity matrix is changing.
But you added to the second one too, right?
Yeah, so this, we did 2 steps in one here. So here's the original A. Here's your identity matrix. So to get rid of the 1 on the bottom row, we're going to do -1 times the first row and add it to the third row. To get that 0 in this second row position, we're going to do -2 times the first row and add it to the second row. So you should get these. And keep in mind, you're doing these all across the row to incorporate the identity matrix. So now the identity matrix is starting to change, right? So what would make, now that you have this resulting number 2, this number 2 result, now what would you do?
Get rid of the 0.
Okay. You would get rid of the what?
0 on the third row.
Okay. How do you?
First row to the third row. Like to get rid of the negative, right?
Yes, you want to start, so we have a leading 1 now here for our first column. How are we going to get a leading 1 for this second column?
2 times the second row.
Mm-hmm. Yeah, so we got -2 times that second row all the way across, add it to the third row. So boom. Now we start to get this. So see how, once again, the identity matrix on the right changed again. See how we're getting that we're going towards reduced row echelon form for that original A on the left. Now what would we do? Yeah, you got that bottom row by -1. So now we get this. Now what do you do?
Jordan. Go back.
Yeah, you got to go back up the matrix. You got to do the second half, which is the Jordan elimination, right? So what do you want to do now?
Use row 3.
Yeah.
The -3 row 2.
So you're gonna do multiply.
Plus row 2.
Yeah, so 3 times the third row, add it to the second row. So here we go. Then you could do more than one step. You could also do -3 times the third row and add it to the first row. So if we did both of those, you should start to get something like this. So what do you notice about this matrix on the left? What are we getting closer and closer to? We're to reduce row echelon, right? And what else? The identity, yeah. So what do we got? We got one more step, right?
Multiply 2 by the second one and add it to.
You got it. So we're going to do -2 times the second row, add it to the first. And boom. So now look at what we have. We have gone through all of our operations. And because we are able to achieve this identity matrix on the left by going through and doing all our reduced row echelon operations. So that means it has all 4 properties, right? And because we were able to achieve the identity matrix, we can say that, yes, guess what? A was invertible. And we have also found the solution for what that inverse is. So now this matrix here on the right side is now the inverse of A. What would happen if you were not able to get that identity matrix on the left? What would you say?
There's no inverse.
Oh, I think I heard it. So it's not, it means it's not invertible. If you can't get to the identity matrix, that means it is not invertible. That might very well happen to you. So let's.
We can't get to it, or like we can't get to it.
Well, that's where you're going to have to make sure you double check your work. So that's one thing you are going to have to be careful of. So just realize that. So here, this is just to give you another example. We're not going to do it all out laboriously, but here's another matrix. Here you have it. You would set up the identity matrix on the right. So now you're going to do all the row operations on both of them together. So then we go here. Then the next one would be here. And along the way, for this particular example, you got a row of zeros. So because you got that row of zeros, it's not going to end up being in the identity matrix form. This particular matrix is going to be not being able to be invertible. So just realize you're going to have your two different methodologies then for your different sizes of matrices. So it's a lot easier to work with a 2x2, huh? Should be able to immediately glance at it and know. This one, you got to do a little bit more work, right? Yes.
This method can be applied to any n by n matrix.
Square, right? They have to be square, right? Because to use this methodology, you have to pair it with an identity matrix. What do we know about identity matrices? They're square, right? Because all they have are the ones
So
on the diagonal.
So you did 1 times the second row added it to the third row, which was zeros on the left side, but how are you getting 1, 1 on the right side?
Okay, so let's go back up to, okay, we started with this. So here we did -2. So if you look over here, -2 times this first row, we add it to the second row. So now there's a 0 here. We do 1 times the first row added to the third row. So now there's this 0. So if you carry out those operations all the way across the row. So is there a particular number in mind?
Also, you just added the -2 to the 0 and the -2 to the 1.
Yeah, so let's look at it. So if we did, let's do, we'll look at the third row first because that's, yeah. So the easier one to visualize is this 1 times. We'll do that one. So look at 1 times the first row up here. So we got 1, 6, 4, 1, 0, 0, right? So we're going to do 1 times that and add it to the third row to create that 0, right? So 1 plus -1 is going to give you a 0. 6 plus 2 is going to give you the 8. 4 plus 5 is going to give you the 9. 1 plus 0 is going to give you this 1. 0 plus 0 is going to give you this 0. 0 plus 1 is going to give you this 1.
Oh, just carry it up.
You got to carry it all the way across. So that's why you're pairing these matrices together. Then you're doing the row operation all the way across both of them. So just keep that in mind. Okay, let's.
Get zeros in any row that's pretty much same length.
Yeah, you're exactly right. If you've gone through and you're doing your Gaussian Jordan elimination, you end up with a row of zeros and you know you did it right. Ding, 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 not invertible. Now, that means a row of zeros on the left here. Yeah. Okay, so that is that one. Okay, so we get to that and all right, so we got all the way down there. We got that row of zeros. All right, so there is something that I want to go back to because I think it is, bless you. All right, I think hopefully this will be these same pages as my book. I hope. Ooh, I hope. Otherwise, dun, 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 dun. Here it is. So to your point, when we're looking at those equivalent statements and we have that AX equals 0, we'll only have the trivial solution. We're going to talk about that for a minute. Yes.
In this case, if we have more than a 2x2 matrix, we won't know if it is invertible onto this original form.
I'm sorry. So if you have a 2x2 matrix.
So unlike we have the 2x2 matrix that we can call the experiment, we know if it is invertible or not. Here, we won't know if it is invertible until we solve the original.
Right. Until you're going through all those different operations. Yeah, we haven't learned a shortcut as of yet.
Bonus points to
We will have some things coming up that'll hopefully maybe help in some cases, other cases not. Yes, go ahead.
And I just said bonus points to whoever finds this short.
Yeah, so hopefully as we get a little bit further, you always want to be kind of making connections. I would really recommend that you guys review these theorems, review the examples. They're good. Okay, so I wanted really quickly, let me see if I can, oh, no. Oh, here it is. Maybe let's try 70. Oh, that's probably too small, huh? Maybe 85? Oop, let's go one more, 90. All right. So I want to revisit this concept again that was in section 1.2. So with this, you know how we've been working with different sets of linear systems, and most of the time they equal some sort of b on the other side of the equal sign, right? Well, if you have a set of equations and they all end up equaling 0, that is going to be a set of homogeneous linear systems, okay? So just keep in mind. Now, if you happen to have a set of homogeneous linear systems here, or linear equations, if you only come up with one solution, then that solution is going to be the trivial solution. And that comes up when x1, x2, and x3, or however many variables you have, they all equal 0. So I think that you can see that, right? Where, you know, if you filled in zeros for all of your variables, obviously 0 is going to equal 0, right? Now, if that is the only solution to this set of linear equations, it is called the trivial solution. However, you know that we have that situation. What's our situation with linear systems? We either have how many solutions?
Zero.
We got either none, we have one,
Or infinite.
or infinite. In the case of homogeneous linear systems, do we ever have none?
No.
No, because we can always put all of the variables equal to 0, and it's always going to equal 0. So we're always going to have at least the trivial solution, right? Now the question is going to be, do we have infinitely many? If we have infinitely many, then those are going to be called non-trivial solutions. So so this is in section 1.2, page 17. So I encourage you to look at this again. Now, just to kind of visualize what that means is here you can kind of think about it. Well, let's pretend you have a set of linear equations, and if they only have the trivial solution, they're going to only have this one point of intersection at 0, because that's the only solution there is. Everything equals 0. Now, if we're working in 2 dimensions, if there's infinitely many, then these lines are going to be concurrent with one another, and they are going to go through 0, 0, because 0, 0 is going to be one of the solutions amongst the infinite many. So that's a really good way to kind of visualize that. So I wanted you guys to see that. So keep that in mind. We do have a certain situation that we call homogeneous linear equations when they all end up equaling 0. So you can either have the trivial solution or non-trivial, which is the infinite many. Okay, so then I'm going to draw your attention to page 34. So we are going to want to look, hopefully it's the same. Okay. Whoop. So the other thing that I want to draw your attention to that's going to be helpful for you is that you also want to realize that you can have a matrix form of a linear equation. Now, we briefly touched on this before, but I want to draw your attention. So this is in section 1.3, page 34. So review this as well. So here we have this set of linear equations, but we can represent this in matrix form. Okay? So just realize that. So what does that look like? So I have shown this to you before. So if you were going to go ahead and put this in matrix form, here you would have all of the equations on the right, or on the left side of the equal sign. You kind of set this up as a matrix, and then you'd have it equal a column matrix of all of your b values. Now you can then further pull that out where you're pulling out all of your x variables out of this matrix and creating your own column matrix of just the x variables, and it can be represented by this. Now, just to show yourself how this would work is you can go back to the original form by multiplying this matrix by this column matrix, right? And you'll end up with this original matrix that you had up here. So you guys see that? So you can multiply this row times this column and be able to get your b value. You can multiply this row by this column, get your b2 value, and then so on and so forth. So your linear equations can be represented in matrix form. So the way that we represent that by a single matrix equation that's going to encompass all of this is that this matrix is going to be your A. This column matrix of your x variables is here represented by the x, and all of that is going to equal your column matrix B. So you can further simplify the representation. So just keep that in mind. So we can represent linear equations in matrix form, and then we can even further end up with a single matrix equation. So this is going to come into play with all like your equivalence statements, because now you're going to be seeing single matrix equations. And you're going to want to know how to manipulate those. So we are going to go ahead and look at, we're going to go back to our original example that we were on. So we were back on page 59. Okay. So here, so we're going to be looking at, where's that equivalence theorem? Okay, it's up here somewhere. Ah, here it is. So now hopefully you have a better understanding of what this AX equals 0 is. So it's telling you that a set of linear equations, of homogeneous linear equations, if they're all represented by this single matrix equation here. So they're telling you that it will only have the trivial solution. So as you can see here, here are some homogeneous linear equations here in our example 6. So how would we write that in this single matrix equation? How would we end up doing that? Does anybody have any ideas based on what I just showed you?
You said do row times that one column?
Yeah. So what you would be doing is we're going to be having here AX equals 0. So if we wanted to put it in that single matrix equation form, what would we have? What would that look like for our matrices? So this A is going to represent your coefficient matrix. So here we would put this as, so what are our coefficients going across? We've got what? 1, 2, 3. And then we've got 2, 5, 3. And then we've got 1, 0, 8. So this is going to be your A. Now, is that an augmented matrix? No. When we are just looking at the coefficients, that is called a coefficient matrix. So keep that in mind. So you are going to want to, then we would be multiplying that by our x1, x2, x3. And all of that then is going to equal what? 0, 0, 0. So this single matrix equation represents this set of matrices, which are all related to this set of linear equations. So here we can go from our linear equations, we can put them into matrix form, and then we can go even further and simplify it down to a single matrix equation.